must first learn a few definitions. The first important definition is critical depth. The critical depth represents the depth representing the minimum energy.
We'll talk about this today.
Critical depth is dependent only on the flow rate and the geometry of the
7
channel,
minutes, I'm
as
not sure we
shown
need
in
it.
the equation. Using the critical depth, we can classify the flow. The first classification is supercritical flow. The flow regime is supercritical when the flow depth is less than the critical depth for the given flow rate and channel geometry. Supercritical flow is generally associated with steeper slopes and mostly occurs in man-made channels. Some examples of supercritical flow are flow in street gutters, flow down a spillway, or flow in steep concrete channels. The second classification of flow is subcritical flow. The flow regime is subcritical when the flow depth is greater than the critical depth for the given flow rate and channel geometry. Subcritical flow is the most common type of flow and is a result of smaller channel slopes. Most natural
First
channels
snow?
have subcritical flow.
First snow ever?
With these two flow regimes now defined, we can define the hydraulic jump. The hydraulic jump occurs when the zone of supercritical flow
First semester in the
discharges into
US?
the zone of
Yeah.
subcritical
In
flow, causing the depth of water to
In the
cross critical
frigid
depth.
north?
The transition between the two flow regimes is associated with a large amount of energy dissipation. Common locations of hydraulic jumps are spillways, where the spillway discharges into the natural channel. It is of interest
Alright.
in engineering to know the ratio of flow depth across the hydraulic jump. This ratio can be computed by momentum conservation across the jump, as shown in the equation. We are now to be checked for loose connections to prevent leakage. You can now start the pump and set the flow rate. The flow rate may be roughly adjusted to the desired flow rate by using the flow rate gauge below the end of the flume. For an accurate reading of the flow rate, use the hydraulic bench and stopwatch to read the volumetric change of water over a different. We can now set the slope on the flume to create the desired normal flow depth.
Greetings.
Since we know the flow rate, we can calculate the critical depth for this flow rate, given a channel width of 76 millimeters. To help us create the hydraulic jump, we can mark critical depth on the side of the flume and use it as a reference point for supercritical and subcritical flow.
Blah, blah, blah.
Take a moment now and think of ways the hydraulic jump could be created in this condition. Since the flow is near critical depth, we can use the stop logs at the end of the flume to create subcritical flow.
So,
Now,
so we'll talk about this today. So I guess the last of our topics is so-called rapidly varying flows. Talked about uniform flows, gradually varying flows, and rapidly varying flows. So I guess we can summarize those, but we'll finish up with talking about this later on. And you've already seen the example of one of these in the YouTube movies from Monday and Wednesday as well. So the idea. And that is that you can get it to transition from this very thin flow of water here to jump, hydraulically jump into a different state. So supercritical flow, it's going faster than the wave speed, surface wave speed.
the sluice gate will back water up behind it. Check to make sure the water level doesn't get too
And
high
downstream
and
becomes
start leaking.
subcritical.
We can now verify the height of the jump by first taking a measurement of the upstream depth, or the depth in the supercritical section. Using this depth and the flow rate, the depth downstream of the jump is calculated.
Yeah. So
This can then be verified with measurement. We are going to increase the slope.
fine. I'm
This can
gonna-
then be verified with measurement.
We might be interested, for instance, to be able to calculate, if we know what the upstream depth is, to be able to figure out exactly what happens downstream. And so maybe we'll do that today with gradually varying flows, take off from where we left last time, and then take the next step into these rapidly varying flows. So that's really all we have to take care of today. So let's try and summarize some of the stuff that we've done so far. Let me do it by writing rather than going through notes. And so just to summarize what we have done so far is, so for uniform flows, which are these, see how good my writing is. We know that the depth with length downstream is constant. And I won't draw the figures for that, but we know that for a channel that has some perimeter attached to it, and has an area attached to it, bless you, suppressed sneeze. This is Y, right? We know that must have it written somewhere. The average velocity is equal to kappa over the Manning coefficient. This is 1 for SI units, multiplied through by the hydraulic radius to the power 2 over 3, I think, and the slope to the square root. So the slope is delta Z over L. And hydraulic radius is just the area over the perimeter. So this is the cross-sectional area here. So it's formulaic. It requires that as we go downstream, it keeps the same depth. Nothing changes as it goes downstream. Constant slope. And in that particular case, the change in depth with length is 0. If we talk about, which we talked about last time, gradually varying flows, then as you see above, dy dx is much less than 1. So depth does change as you go downstream. And I guess what we did was we took this particular geometry and we defined a flow rate that was present within a unit width of this, 1 meter or 1 feet wide. And so Q is in meters squared per second. No, it's meters cubed per second divided by length. And if we did that, we could take the energy equation which you know is Z1 plus P1 over gamma plus V1 squared over 2G is equal to downstream 2. You must be sick of this equation by now, but I guess it might stick in your mind. It's useful if it does. Plus head loss, right? And what we could do was that we first of all wrote the fact that we could define this velocity in terms of this flow rate. I won't do it again. And we could take the elevation term off to the left-hand side. And we could rewrite it as energy upstream is equal to energy downstream plus head loss minus slope of the bed multiplied by length. And so if we draw a section which is of some length given here between points 1 and 2, the depth length of flow downstream is this. This, of course, is delta Z, and the water on top of there would be flowing at some rate here. So this would be Y1, kind of parallel to the bed, but the slope is so gentle that it doesn't really matter whether it's vertical or perpendicular to the bed. And I guess this might be the energy grade line. And so this term here would be V1 squared over 2G. And this term here, which I guess really should be vertical, is V2 squared over 2G. And the horizontal line for constant energy would be this, and this would be head loss. Right? So this would be, I guess, the hydraulic grade line. We've seen all these terms before. This is the water surface going downstream. So that's so by definition, these terms here are equal to the head loss divided by L. And this term here is, it's negative, so it's, well, it's better. This is slope, which is equal to delta Z over L. And this is delta Z, right? And these individual terms we wrote, we would include them in terms of these two components. We wrote this as being equal to the depth, Y1, right, which is just the static depth of fluid. And then each of these terms would be E is equal, bless you, Y plus Q squared over 2GY squared. And so this was the key change, was that we wrote the velocity in terms of a flow rate per unit width, because for the system, even if the height of the flow changes, that will be accommodated in this. Every single rectangle downstream, as you go downstream, the rectangle you have downstream for a gradually varying flow, even if the height is different, the total flow within that width has to be the same, has to be conserved. So that was the rationale for doing that. And so the important thing with this was it allowed us to be able to just draw this energy versus depth diagram. And we'll spend 2 seconds playing around with that this morning. So this is depth, Y. This is energy, E. And the ordinates on this figure were, there's a line that's y equals e, which is 1 to 1. And then there's a line, and I can't draw these very well, this nose that we had. It's probably a bit shallower at the bottom. Oops. My bad drawing. Oh, Jesus Christ. That's not bad. And we had some ordinates on this. So this point here was where the Froude number equals 1. This was Froude number less than 1, so-called subcritical. And this was Froude number greater than 1, so-called supercritical. And I guess we also talked about the ordinates of this point was, this was the minimum energy. And this was a so-called critical depth, which you just saw on the video, the hydraulic jump. And I think E min is equal to 3 over 2 times YC. Not Y2, YC. Yeah, so that kind of summarizes what we did last time. And so the important point was that if we sit at some kind of flow, so you can get this curve if you know that Q is equal to 5 meters per second, meters squared per second, then you can calculate E is equal to Y plus Q squared over 2G Y squared, just by taking Y equals 0, which would be this point here, then 1, then 2 to 10. And that allows you, that would allow you to get all of these individual points here. So you'd be able to, you can construct this curve merely by plugging and chugging some numbers. And then you can use this to be able to play around and determine what flow regimes you'd find yourself in. And we kind of skipped over that last time, but let's go back a little bit and talk about, we don't need to talk about everything in here, we'll talk about very little. But I guess we talked about this, was this the one? Yeah, let's do this one and this one, yeah. So this is the idea here, is if you, so there's too many things on this. But so here is your, maybe this is 5 meters squared a second for this particular one here. So physically what this means is if you had a flow and you constrict the flow with a gate so that you have the height of the flow that's upstream, then for this particular energy of the flow that you have going downstream, the upstream height depth would be this, just going across here. It comes out of the bottom, and at the bottom, the flow would be constrained by this curve, which is the middle curve. And because they're the same energy on this vertical line here, then the depth of flow in the downstream portion has to be this. And so what you can do, you could imagine playing around with some things. If you plot, say, for 7.5 meters squared a second, and you go through this same calibration for energy is equal to Y plus Q squared over 2G Y squared. So you can cycle for a different value of Q, some different values of Y, and you'd come up with a new curve. If the flow was larger, it would be on this inner curve. And if the flow rate was smaller, you'd be on this smaller curve. And so the games you can play with that would be to do this. Did I do this last time? Can I get rid of these? So our original plot we had was this one here from above. So this represented us putting a sluice gate so that, well, I guess I'm just going to redraw it. So that the flow between these 2 points was this and would represent a gate that looks like this. And so this would be Y2, and this would be Y1. So you could do a thought example to say what you would do if you did these two things. So if you raise the upstream level, so Y1 goes up, but you stay at the constant flow rate, so the flow rate stays constant, what would you have to do that? You'd have to lower the gap to do that. So you increase the upstream head that's driving the flow, and that would give you a larger flow. To staunch that flow, you lower the bottom of the gate. And so if you did that, then what you would do is that you'd still be on the same curve, which is, this is Q0, this curve here. But you're raising the upstream level by raising the gate. And since you then have the energy defined by this vertical line here, to keep the flow rate the same, you'd actually have to lower the gate by this small amount here that you can barely see perhaps. It's a width of a pen to go here. So by taking this gate and extending it so that the water level upstream can go up, you need to be able to reduce the increased flow that you'd get naturally by having a higher driving head, by having more constriction at the bottom. So you'd move from point 1 to 1 prime because of the upstream higher head, and you'd move from point 2 to 2 prime because you have to drop the bottom of the gate to be able to staunch the flow. So that's one game that you can play. If you alternatively want to raise the upstream level to another height, double prime, that would naturally increase the flow rate if you don't do anything to the gap at the bottom. So if you don't lower the gap, but just raise the upstream level, then you'd migrate onto a different curve. So you'd migrate onto the curve which is now this red curve. So this red curve, Q is greater than Q0. You'd raise the upstream head from 1 to 1 double prime. So this is, you're raising the level of the water upstream to here. If you're able to maintain it on this curve, Q0, then you just migrate on Q0. You see they're roughly the same anyway, but you're actually migrating on a higher flow rate, so you're really on this curve here. They're roughly the same because you remember that this line here is 1 to 1, and so they converge on here. And so you're sitting at this point here. So this now is the new energy that you find yourself working at. And so if you haven't lowered the gate to stop the flow, then you migrate to this point here. So this is the higher flow, volumetric flow rate on this curve. You've increased the height of flow, higher driving potential, but you haven't reduced the constriction at the bottom, and so the flow rate goes up, so you switch from this Q0 curve onto another curve to do that. And so that's physically all that this means. A bit complicated when you're drawing it out, but not particularly so. So the other game you can play is epitomized by this idea here. And that is, if you have an upstream flow, then you know that height and you know that flow rate or flow velocity. How do you predict what's going to happen downstream if you have either a ramp or a bump in the flow? And so what we need to do is go back to our expression, which was upstream energy is equal to downstream energy plus, I guess we could take Z1 off the other side, right? Just by moving it. So we have E1 is equal to E2 plus Z2 minus Z1 if we ignore the head losses in the system. And so if we want to figure out exactly what's happening downstream, we could write this in terms of E2, the energy downstream, just by rearranging it. So it'd be equal to the energy 1, and this would be Z2 minus Z1. So this is this is positive if it's being risen, if it's rising. So this is larger than this, so this would be positive. So let's subtract it off the left-hand side as delta Z. So this would be the positive height change we have that we're subtracting off. We'd like to know what this is if we have this. So we can do our specific energy depth diagram for that particular flow rate. So it'd be for a given value of y and a given value of q. So it's in English units, 2.3 feet, and there's a velocity of 2.5 feet per second. So we can calculate q from that directly and then make this curve. So this curve would be 2.5 feet, so what is it? Is there a given width on here? Yeah, fine, given flow rate. This is your given flow rate. So you could put in y equals 0, 1, 2, 3, etc. And you'd end up getting these individual points, whoops, here. And if you did more of those points, you'd get a full curve. And then you can calculate exactly where you are in terms of the behavior. So you know that upstream, it's 2.3 meters depth. So the upstream depth, if you plotted it, would be this point here, number 1. So this is where you sit for the flow. You know that as you go downstream, you conserve energy. So the energy at this particular point, I think, this is 2, this is 3, this is the energy of point 1 upstream is equal to 2.4 feet. Lengths, they're both in lengths that are given. And so if you go up a ramp of 0.5 feet, you can imagine that what you're doing is you're moving this direction 0.5 feet, right? So this is E1, which we have. We want to calculate what E2 is, and that will allow us to calculate the depth. And so we subtract off E1. I guess this is minus. I wrote it just by moving this around. So we're subtracting off an amount 0.5 from 2.4, and we'd find out that the energy at this particular location downstream is that. And so what that means is that if we subtract off 0.5, we're either sitting at this point here or this point here. And we know that to get from one, so I'm misdrawing it, I guess, right? It's on, yeah, this point here. So we start off at 1, we want to get to 2 or 2. If we want to get to this one, we've got to go all the way down this and around this nose and get that. But we don't have a big enough change in the energy to hit the nose and come on down. So we're restricted to being on this side of the curve. If we want to get to this side of the curve, then what we need to do is have a ramp that instead of being 0.5 feet tall, allows us to get to this point here. And so the size of the ramp that we need, which is shown here, is just given by this length. the length to the nose. And it's already marked on here as this is 1.51, so the difference here is 2.4 to get to 1.51, I guess is 0.89, right? And so if you want to be able to get to this nose, then what you need to do is to get to this point here. And then once you're at this point here, this would be the conditions. So you'd be flowing at this volumetric flow rate. The depth of the flow would be equal to YC, which is 1 foot. So this would be YC, if you can see that. And then downstream of that, it has the option, since you're going back down again to whatever this elevation was, which was 0.5 of a feet above the baseline, you're going back to get to the same curve here. And so you're sitting here at this point here as you're on the bump. The depth of the flow is the critical depth, YC. And then you have a choice as you go downstream. It could either be subcritical by getting large and being this point, or it could be supercritical and going to this other point to above it. You have that choice. But you can only get to this point if you do go through, if you have the bump to be able to drive that flow. So that's the utility of these curves, to be able to do that. And so I'm not sure. There's a whole lot of calculations after this, which I don't really want to go through because I don't think we need to. But that sets you up with what you essentially need for the things that we're talking about. And then I suppose the last thing that we might want to deal with today is so-called rapidly varying flows, where the change in depth changes a lot as you go downstream, and it's epitomized by what we looked at in terms of these hydraulic jumps. So this is where we were before. So let's briefly look at rapidly varying flows. It follows along from the movie we looked at for hydraulic jumps. And the deal is that if you have flows which are flowing at quite high velocities, so supercritical flows, sometimes they're unstable. So if you do something to it, like have a bump in the bed of the flow, or some small perturbation, all of a sudden it triggers this, I guess kayakers would call it a pile up of water, that it slows down to subcritical flows, and as a result backs up, so that when you talk about dy dx, approximately to 1, that's saying that this slope here is exactly what this is. This is dy, and this is dx. I guess it is positive 1 if it's downstream. If this is x, and this is y. And so how do we deal with that? And so I won't belabor all the analysis that you might apply, but we've seen this before when we talked even about uniform flows. We took the momentum equation and we said that the momentum equation would give us, it's just a force balance, right? This is just equal to F equals MA. This here is mass flow rate, this is velocity, and this is force. And so all we need to do is take the force diagrams upstream and downstream. So I'll just explain where the terms come from. And so force 1 would be this. I guess it's useful because we're actually using everything we've used or derived in this class. The force is this triangular distribution, which is a half unit weight times the thickness into the page of the reservoir, of the flow, and the y squared, the depth squared. So you remember that the force is equal to the height of the centroid times unit weight times the area. This is exactly what this is. Height of the centroid is half height, looking onto it. Unit weight is here, and the area is b times y, and the other y is the centroid depth, which is a half the depth, right? So this term is just the force. Force 1 minus force 2. Before we said that they must balance. If the depth as you go downstream is the same, then these force triangles are exactly the same. So the forces would balance. Also, if the depths are the same, the downstream velocities and upstream velocities are the same as well. So this term ends up being 0. So you had 0 equals 0 for uniform flows. Not the case if velocity is changing. And so if we write this out in terms of the velocities, again, we write the velocities in terms of a flow rate per unit width and substitute that into here. And if we do that, we get a term which is this equation. It's kind of like, it's almost like an E1 equals E2, but don't write that, well, instead of writing that, let's call it M1 minus M2, or M1 equals M2. And so this is a measure of the momentum that the fluid has as it goes through the system. And so we can define, instead of the energy, we can define the kinetic, the momentum in the system. Instead of energy, we define the momentum in the system. And we know that we conserve momentum when we go from upstream to downstream. We don't necessarily conserve energy because we might have energy losses in the system. And so I guess I should talk about the fact that what we're doing is we're going from upstream to downstream. We have a depth upstream and a depth downstream. From the energy grade line, which would be the depth plus, I guess this would be v squared over 2g, right? To the same down here. We have a change in energy because we have a loss in the system. We have these big vortices that are developing, which eat up all the energy in the system as we're flowing downstream by recirculating the water. So what we don't know is the magnitude of the head loss in the system. It's not very easy to determine. So we don't know that when we go from upstream to downstream, we're no longer on the same energy grade line. And so we don't know what this is. That's exactly our problem. HL equals question mark. But we know that momentum must be conserved, and so we know that this must be true as we go from upstream to downstream. So we have an equation that defines momentum upstream and downstream. We can apply continuity upstream and downstream. So this would be just Q1B equals Q2B, right? Flow rate is the flow within this thin slither that is 1 meter or 1 foot wide. And so this is just the Q1 is just the product of Y1B here. So this is true. And so we have an energy equation, but the problem is we don't know this. And so what we can do is we can, in a diagrammatic way, I think it's a pretty good diagram actually, is that we can think about energy and also plotting momentum. You see that momentum equation is not so different from the energy equation. Instead of y1 q1 squared over 2g, so what was it? This is y plus q squared over 2g y squared. So this is the energy equation. We said that if we set this equal to 0, then you'd have to multiply both sides by y squared. You'd get rid of this y squared. This would become y cubed, and this would become y squared. And so it's a cubic equation that has 3 roots, and we know that it looks a bit like this. We can do that. This momentum equation isn't all that different, except this y term is now y squared. This y term is just y instead of y squared. And so again, we have a very similar relationship. So if we went through this and we calculated what m was as a function of y equals 0, 1, 2, 3, etc. Then we get a diagram that happens to look very similar. So if we have a given flow rate for a momentum diagram, we plot depth versus momentum. We have this system here. And so now, in the same way as we had before, these depths here, if we have a given momentum value, which we could calculate for our system, we would have two possible supercritical, subcritical, and supercritical flows, upstream and downstream, and they'd correspond to these particular depths here. That's all we're saying. The depth of the flow is equal to this. So now what we can do is we can go over with those depths onto this diagram, onto the same flow rate, and we'd see that if we do that, we're actually not at the same energy for the system. In fact, there's a change in energy as we go down from upstream, where the energy is higher, to downstream, where the energy is lower. We get a change in energy in the system, and this change in energy has to be equal to the head loss. So a quirky little change, but only in this particular case to be able to define exactly what the magnitude of head loss is. And so that may seem kind of esoteric, but our reason for doing that, and I won't go through this, is that it allows us, if we have some manipulation, to be able to take the system that's flowing on the bottom of a region like this. And if we have a depth of flow in the upstream portion and a depth of flow in the downstream portion, then we can define this term here as a function of a known upstream portion. So this would be supercritical, and it would have a Froude number, which is equal to V1 over square root Y1G. So we can get the magnitude of this. We can get the magnitude of the upstream depth. And as a result of that, we can calculate what the downstream depth would be, which would be larger because it's subcritical. Because as you see here, both of these points are on either side of the nose, which is FR equals 0. So this is larger below and smaller above. And that might seem esoteric, except for the fact that if you, again, figure out what the parameterization of this is that if you know the magnitude of the Froude number, and you know the upstream depth, you can calculate what the downstream depth was. So cases where you don't have a jump, cases where the jump is large, larger, larger, largest, defining the magnitude and exactly what it looks like. So that's it. And that is probably it for rapidly varying flows. So we've covered all three. So I guess I don't know that we need to define it here, but for rapidly varying flows, I'm not sure actually what I need to write other than just summarizing the fact that momentum's conserved, energy is conserved as well. But HL unknown. So that's essentially what we did. So we can calculate momentum balance in the system. We calculate that in terms of this uppercase M value that we just described. If we know the upstream velocity and we know the depth of flow upstream, and therefore we also know the Froude number, then we can calculate the head loss as we go downstream. So that's it. So that is it. So that's all we'll cover for open channel flows. The stuff we've talked about today in the first part is probably useful to you in the closeout of the class. The second stuff that we talked on, rapidly varying flows, is useful to you, but not in the closeout of the class. So just so you don't necessarily have to look at that. So I think there's a gradually varying flow. So you should know how to work this diagram. And all the questions, as I said last time, are actually repeats of previous questions over the years. So if I were getting ready for this, I would just go through the solutions, see if you can rationalize how those solutions exist, and then that would be the best preparation. That's it. I'll be around this week, and well, the week's over. I'll be around next week if you want to swing by. I think Matt will be giving the test, so come by, see me. Happy hunting on the 3 Monday, Wednesday, and Friday. You know what the material is. All retreads of previous questions. Monday is a pipe flow network question. Wednesday is an external flow question, balancing forces to get terminal velocities, I think it is. I think you know that. And the final one is something on gradually varying flows. And yeah, you'll have seen them all in the prior midterms. Great. Questions? Going to finish 5 minutes early? No questions? Not a single question all term long? No. Ah!
Sorry question, but thank you so much.
Okay, thank you. You're very welcome. You've been an enjoyable class. Thanks for coming. It's been quite a big class compared to previous years. We had maybe 15%. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 20? That's more than 20%. I think we have 88 people in this class, as you see when you come to take the test. Good. Well, great. Good luck next week. And if I don't see you before the break, I might see some of you in contaminant hydrology if you're environmental systems engineers in your very last semester on campus. You take that class. Great. Take care. Bye-bye.